Hi everyone, my name is Shardul Vaidya, and today we're going to be talking about dark factories, the step beyond agentic engineering. The term dark factories itself comes from manufacturing, essentially a factory that has absolutely no humans at all. Requirements go in, or essentially raw materials go in, and a finished product comes out, no humans involved at all. And the intention is, well, if humans are not needed, then why keep the lights on? Let's look at agentic engineering by the numbers. When an engineer presses trust all tools or YOLO or non-interactive, as I like to use it, you see very often a 53% accuracy decline. That's essentially where an AI has no feedback loop. It has no way to know that it's gone wrong. On the other side, we have this 91% versus 25%, where 91% of engineering leaders claim that AI has improved velocity, but only 25% have the data to prove it. And one of the fundamental reasons for that is the prevailing approach. You get the standard enterprise rollouts, buy seats, try for acceptance rates, declare that you're done. Or you look at developer productivity metrics. These are lines of code, PRs per sprint, essentially just looking for higher velocity, but not necessarily improved product quality. The next thing you see most often is prompt engineering training. This is essentially teaching developers how to talk to models. This has a very short shelf life, 12 months at the time of recording, but honestly coming lower with models being released every other week or every 4 weeks even. And the last thing is the AI Center of Excellence. These are committees that meet every month, discuss what shipped, and then see if they want to make any decisions to move the enterprise forward. This, I don't think, is the way. The gap fundamentally isn't productivity. It's an architectural imbalance. One approach assumes that humans stay in the loop and AI helps make them faster. The other assumes that humans are responsible for the verification and a system design, essentially instilling organizational best practices into code. Verification systems replace their judgment. These aren't even same points on the agentic engineering spectrum. One scales with headcount, where humans essentially still are the bottleneck, code review remains the bottleneck, and the other scales with just a raw amount of compute. We're seeing the frontier move. A handful of companies are already operating at this dark factory scale, but let's talk about it a little more. Same idea as the SAE levels for self-driving, each level is fundamentally defined by what a verification system is trusted to do. Can you fundamentally remove the human? Level 2 needs something like lane keep cameras. Level 4 needs LiDAR and redundant compute. In the case of code, level 2, we're mostly focusing on unit tests and lints and automated test writing and automated test execution. But to truly get to level 4 or level 5, we need the agents to have an incredible amount of trust in the system that's providing back pressure to them. And that essentially means that when the reviewer says, hey, this is wrong, the agent is forced to listen. Every major model can write solid code for a well-specified task. That's been true for over a year. The gap between level 2 and level 4 isn't model access, it's what you trust the model to write without a human reading every diff. So let's talk about who's actually there. The Coinbase or ramp convergence is the strongest evidence for the architecture that we're going to talk about soon. These are two independent companies that essentially don't talk to each other but independently arrived at the same pattern. This is constraint-driven design at its finest. And StrongDM essentially came up with this full digital twin universe that simulates everything surrounding their prod environment. They have end-to-end scenario testing already built in with LLMs, and they approach it with the fundamental idea that zero humans write code, zero humans review code. Coinbase Ramp, Stripe, Anthropic, and StrongDM all came to the same pattern. Isolated sandboxes, curated tool sets, sub-agent orchestration, and most importantly, verification gates that provide immense back pressure to the coding agents to write the correct code. This is the same way that we've seen web-scale data constraints produce MapReduce. And let me show you what that looks like. This is what I think the baseline dark factory architecture looks like. You have some kind of orchestrator whose sole responsibility is to decompose, convert it into a DAG, and then dispatch into coding agents, right? The decomposition happens with a planning pattern. It doesn't matter where it gets the requirements from. It can be from Slack, it can be from Linear, it can be from GitHub, or it can even be by just typing into a web UI. But once you get that, you decompose it into a list of tasks while the planner has access and ability to research the codebase. This is exactly what you would do in a planning sprint or a planning meeting. And then each agent, each coding agent is given its own sandbox, it's given its own work tree. And in the case of like hyperscale, you would probably give it its own container to live in. And then once it thinks it's done, we go through some kind of a verification gate. We're going to talk about verification gates in a minute, but it goes through some kind of verification gate. If it fails, it goes through rework, goes back to the orchestrator, and gets dispatched back into an agent saying, hey, this is what the previous agent did, this is what it did wrong, please fix it. If it gets passed, it just goes onto a merge state where it goes and gets deployed. Let's talk about these runtimes for a second. The key part here is isolation, right? These are essentially highly untrusted systems. They get their own sandboxed, done through a container, a micro VM, whatever your enterprise has expertise in. Then the most important thing after that is context boundaries. There are no shared state between agents running at any given time. This means that these agents are completely stateless. They can crash, we can reboot them, and they will just keep running. The tool registries is what lets us essentially evolve the factory over time. These can be internal tools that maybe abstract away testing, or can be external tools that give access to documentation. But these are essentially standardized. And finally, crashing is a feature. You never run into situations where an agent essentially dies and then is left there to just sort of be orphaned. But if an agent dies, we clean up, essentially leave the state that it was in, and boot up another agent to launch in its place. Spin up, execute, produce some artifacts, and terminate. Then let's talk about how this multi-agent orchestration is possible. First things first, decomposition, the planning stage, so to speak, is what lets us parallelize our processes to the fullest. Bad decomposition can produce merge conflicts because more than one agent will try to do the same thing. And this is where we get our first back pressure. Second, the rework loop is the biggest key. When a task fails, the full context of why it failed is fed forward into the next attempt. That's not a retry, that's essentially just a full rework. Cost optimized routing essentially lets the planner delegate to the correct agent downstream that essentially, this is a trivial task, you can use a low cost model to do it. This is a difficult task, use the high quality model. And concurrent dispatch is what lets us essentially leverage the DAG to say, these tasks are unblocked, you can execute them. Then there's the verification architecture, as we said earlier. Traditionally, even as humans work, we've relied on unit tests, on property tests, on mutation tests to make sure that the code we're writing is accurate, is trustworthy, is going in the right direction. These are all excellent because LLMs have learned from them, right? They know how unit test works. They know how test coverage works. So we use them. We continue to use them. Then we come to the AI native level. Now, I know these are shown as separate streams, but they all happen parallelly, right? There's no one without the other. The most amazing thing that we can do with AI native testing is scenario testing. You can essentially describe this end user journey to your agent and see how long it takes to get to that journey. This is kind of built in user acceptance tests that we previously did not really have access to. And then the last here is the formal and the aspirational side. It's the idea that instead of just making a plan and making tasks, we make a plan and then we make these system invariants that define and declare mathematically what states the system can live in. This is mostly unexplored, and I believe this is aspirational for me too, but this is something that can really formalize how a system is going to behave, and it lets you have immense levels of trust on your dark factory generated code. So let's see it run. This is my factory, and it essentially is a giant monolith that goes from requirements to plan to tasks to execution to merging. And I'll just show off every step of that process. This is my factory dashboard. It essentially has everything that the factory has ever done, including all the projects that it manages. So we can go out here, we can see a health check, we can see if something is broken, but the most important thing in how we essentially give the factory a task is through the submit requirement thing. We select which project this is about, type in our requirements, and hit plan down here. Once that happens, we go into the plan stage. We go into the requirement stage because a plan generates requirements, and we have these essentially context-aware, well-researched tasks, right? So we can click here, which is one of my code review tasks, and we can go down to the actual design. And you can see here that the prompt I provided was very trivial. It's like, hey, we've done a bunch of code review, solve all of the requests from the code review. And you can see that it's generated, I don't know, about 20 something tasks. Yeah, about 23 tasks. And we get this beautiful DAG that defines what needs to be done in what order. And you can see here, we've got some independent lines, we've got some deeply dependent lines, and then we've got some like one-off things that just needed to be sorted. And this essentially allows high level of parallelism in things that have no blockers, just like how human teams are designed, just like how sprints are designed. We're not ripping out the conventional SDLC, we're saying a factory can augment it basically infinitely. And once we go from there, once a plan is triggered, we go into this state where essentially the orchestrator is now treating this as an assembly line. And you can see here we get this like merge status and these like stable change IDs. These are derived from the underlying Git substrate we use, which is Jujitsu. And those stable change IDs let us essentially refer to these tasks stably throughout the history of the project. And then you can see a whole bunch of these are merged, and then we have some failures that say, hey, we've exceeded max rework count. And that's essentially an escalation to me saying, hey, you should probably look at this yourself as a human because you're responsible for the code that it generates. But you can see a vast majority of these are already merged and already ready to go. And this actually, as a matter of fact, this whole UI that you're seeing right now was built entirely by the factory. And we can go look at the code for a minute. We can go down to the factory, and you can see here there's over 300 commits that are essentially very tight requirements down to, right, oh, hey, it's just 3 additions, 6 deletions, net reduction in entropy. And we can force the factory to behave that way. And we can also see this, 27 additions, 30 deletions, very tight, very clean refactor on exactly what's going on. This is what this kind of task decomposition planning into design, into execution lets us do. And the reason it works is due to back pressure. Back pressure in our factory comes in 2 specific ways: the plan reviewer and then the code reviewer. And then there's a deterministic back pressure from the test executor. So in our factory, it's essentially 6 phases that form the pipeline. First, we have the requirement coming in from us, as we saw, then the plan adversary. This is essentially something that reviews the plan generated and the DAG generated to make sure it will work fine within the context of the code base. Once the plan adversary approves a plan, it gets put in the queue, which is managed by our orchestrator. And then once a task's dependencies are ready, we can schedule the task. This goes to the coder. And then this works essentially in an isolated sandbox. We're going to discuss that in a little bit. Once we get through code, once the coder thinks it's done, we essentially run the tests that are configured for our project, and then we go to the code adversary. And this is essentially a code reviewer. It goes through all the code that was written, it looks at the diffs essentially, and then points out if there was too much entropy, if there was like something wasn't done right or some features incomplete. And obviously, if the tests fail, we never get to the code reviewer. This is essentially how a maintainer would refuse to look at a PR if the tests are red, right? If you're breaking something, I don't even want to look at it. And then once the code adversary says it's okay, we go into the merge. This is enabled by Jujitsu's conflict detection, and we essentially have this fine-tuned deterministic merge system. And then if that fails, if there's too many conflicts, we obviously go back out to the LLM, and we actually have a merge rework manager that runs within the merge agent. The isolation philosophy comes from two things, right? First, we obviously want to reduce the blast radius if a agent goes haywire. That's mainly provided by running these in isolated sandboxes. That can obviously be in Docker or in containers. That can also be on separate EC2 instances. However, you like to manage your isolation. The second tier of isolation comes at the version control level. So this is in my factory provided by Jujitsu workspaces. This is the equivalent of Git work trees, but with a little more Jujitsu features. And all of that just allows clean merging back to trunk whenever it's ready to go. The result of all of this is you're no longer writing code. You're composing the factory that writes the code for you. You essentially go from being an engineer who super focuses on code to an engineer who focuses on how the system verifies and fact checks that the code written by the LLMs is correct. You essentially define these really deep requirements, curate the agent's toolsets, architect verification frameworks, and fundamentally ensure correctness. You're responsible for it, but without actually writing every line. So how would we build this on AWS? You can obviously build it from scratch using EC2 and just write everything as a single monolith like I did. But every layer of this architecture has an AWS feature or service that can make it easier to run. Bedrock Agent Core if you want to run long-lived agents, Lambda, Fargate for isolated agent runtimes, Code Build and Code Pipeline for application verification, Lambda for reaching out to external services through tools. All of this can be done through Bedrock. And actually, if you wanted to not even write code for the orchestrator, you could use stuff like event bridge and step functions to just define your factory as infrastructure. And because it's all in AWS, it gives you access to CloudWatch and CloudTrail. Along with IAM, that gives you really fine-grained control of everything and anything your agent can do. And because we might want our factory to be fundamentally stateless, we can store all our state in DynamoDB. And that's how my factory is built. Everything is JSON, so it can very cleanly move into DynamoDB. And once you've done all of this, software writes itself, courtesy of the Dark Factory. These are some of the references that inspired me on the Dark Factory journey. There's Jeffrey Huntley's article on the Ralph loop, which essentially allows you to stack while loops on top of another. There's Strong DM's blog and live website on their factory, and Steve Yege's article on Gastown, where he describes work as these beads that are run through the factory until they are finished. A huge shout out to the Background Agents Summit, and thank you. My name is Shardul Vaidya. You can find me on my email address or on LinkedIn or even on my personal website.